ordinary differential equation or differential equation are many types, but for this particular topic, we are going to look at this just simple ordinary differential equation. Now, up till now, you have whatever equations you have solved dy over dx equal to some value in which you have differentiated or integrated to get some answer. When all of these differentiation procedures were done on those equations, the only thing you did was to differentiate it with respect to x. So it was never, in any of the examples previously, it was never done that you were supposed to differentiate an equation with respect to x as well as respect to another term. It was always with differentiation with respect to x. When you are differentiating an equation with respect to just one variable that is x, which is in this case only independent variable, then such equations are called ordinary differential equations. So ordinary differential equations are the one in which you have only one independent variable. For example, on the screen, you can see a simple equation. Now, forget the actual constants, okay, or the terms involved. Here, this dt by dt, it's a capital T is representing temperature and small t is representing time. So this equation is differential equation of temperature with respect to time. And as you can see, this is what I'm talking about the left hand side, that capital T is the temperature and small t is the time. On the right hand side, K is the constant, okay, any constant. We'll come to the number side of these things in the later slide, but the first I wanted to introduce the concept, and then this constant K is multiplied to the difference of the temperature terms. So these T naught minus T are the temperature terms. So by looking at it, you can already see that the equation consists of temperature with respect to time. So somewhere the process is such that this temperature is changing with respect to time. T naught is of course the initial value, and minus T, that T is some value after some time. So at t equals to 0, the value is T naught, and minus T is some value after some period of time. So, but in this case, this equation that I have just explained, you can see that this equation requires us to differentiate with respect to time only. So as you can see that this equation is an ordinary differential equation of first order. Yeah. Now, and this is what I have just explained to you, that the example shows that unknown function, the function that we are trying to determine, I hope now you are aware what the function is. It was fx, okay, and x was the independent variable. In the example that I have shown, the function is ft because the temperature thing is there. The time thing is there. So the temperature is a function of time, and the equation involves d by dt. So this d by dt is the first order ordinary differential equation. Sometimes you just write it as first order derivative. You don't use the word ordinary. The word ordinary is actually representing that it's just it has just got one independent variables. Now let's give some other examples. So now in terms of just now whatever example that I gave earlier was something that was coming from an engineering point of view. Now in typical mathematics way, and taking an example similar to what you may have done, what you did in your semester 1 differentiation topic, dy by dx equals to 2xy. Dy by dx, you actually solved this dy by dx, and when you differentiate this dy by dx, that is, you differentiate y with respect to x, then your answer is 2y. So in this case, what you can see is that this value or the function is just dependent upon x. Then there is this another example, and this is a slightly different or difficult example, but here you can see that this whole equation has got only one independent variable, and that is x. So the thing that you differentiate with respect to that is the independent variable. So here you are differentiating with respect to x, hence that's a independent variable. The last one is d square y over dx square plus dy by dx plus y. Now this y can be any function of x. What you should focus on is that the term that is there in the denominator, the term with respect to which you are differentiating the function. So in all the three cases, you can see that all these y's, which are function of x, are differentiated with respect to dx. So the independent variable, first, there is only one independent variable, and that independent variable is x. So these sort of equations are called ordinary differential equations. Now, another thing that needs to be explained, the order of the differential equation. Now, when I talk, or you will talk about order of differential equation, the order means the highest derivative in the equation. So if you look at all these three, the first two, this is dy by dx and this is dy by dx, they are first order differential equation because the highest order of that is of dy is 1. Whereas the last example that I shown you, it is d square y by dx square. So this d square, that makes this equation as a second order differential equation. I hope this point is clear. Ordinary equation can be first order equation, second order equation, third order equation, and so on. And that only means that the order of the derivative, you need to look at the order of the derivative, which in first two cases, as you can see, is 1. So it is dy by dx, so the order is 1. And in the last example, as you can see that the order is d square y. So this d square means it is second order differential equation. Compared to this, there is another term which you are already aware of, that is degree. The degree is the exponent of the highest derivative. So the degree is the exponent of the highest derivative. So you need to look at, for example, this dx square. So this dx square, the exponent here is this square. Whereas this over here, it is order, and over here it is exponent. Just to make this clear again, that in this case it is first order, and the exponent here of x and y is 1. Whereas in this case it is second order, and the exponent of dx square. So this dx square, so this square is representing the exponent of the highest order. Now compared to this ordinary differential equation, we also have got another type of differential equation, and it is called partial differential equations. Partial differential equations are those which have got more than one independent variable. For example, the simplest of example is, let's say we have got a rod, a metallic rod, and that metallic rod is heated with respect to time. Now the changes will happen in the rod in two ways. The first thing is that the temperature of the rod will increase. Okay, and the other thing, and now I'm talking about a little physical sense. In the physical sense, just to make a relation, that when you will heat up that rod, there will be two things that will be happening to that rod. One, that is the temperature of that rod will increase. Okay, and another thing is that the rod will expand. Okay, so now you have got two changes coming in a metallic rod. So this was just an example of partial differential equation. In this case, you have got two independent variables. Why? Because there is change in the temperature. Let's say the rod was room temperature at the start before you start heating the rod, and after time, let's say 5 minutes later, the temperature has gone above. Yeah, so now your rod is heated. So that is one change. And the other change is the length, which is because of the temperature. So in such case, when you are looking at things which are changing with different parameters, then in those cases, we usually use partial differential equations. So in terms of mathematics, you always write partial differential equation with Dava. Now this is a Greek or Roman numeral and symbol, and it is called Dava, not D. So when you use D, that is ordinary differential for ordinary differential equation. When you are using partial derivative, then you use the word Dava. So it is Dava u by Dava x minus 3 Dava u by Dava y plus 1. So this is just a simple equation, but now that D is being replaced by the term Dava. Another example, I will come to the order and exponent again, that this equation that actually you see over here. So if you look at both these equations, what I have just explained to you was, let's say that this u is actually a function of temperature. So if this u is a function of temperature, then the changing will occur with respect to x. X is the length, okay, in terms of length, and Dava square u by Dava t square. So this t is representing that time period. So this is just an engineering application of partial differential equation. What you need to look at, that in this case, consider the difference between this equation, this equation and the previous one. Here you will see that now your differentiation has to take place with respect to x and respect to another variable, which is time or t. So in the denominator, earlier for ordinary differential equation, it was just one variable. Now in the partial differential equation, you have got more than one independent variable. That is, here in example, it is x and time t. So this equation, whatever phenomena that I have explained, physical phenomena explained, can be represented by this partial differential equation. So any change that will come in the length because of the expansion of the rod will be represented by this part of the equation, and any change in the temperature of the rod that will come because of the heating will be represented by this part of the equation. I hope that this ordinary and partial differential equation concept is clear. Just to repeat it again, that partial differential equations are the equations in which you have got more than one independent variables. For example, in this case, the example that I have explained, it is the temperature is causing change the temperature is changed with respect to x and with respect to time. So this equation is representing partial form of differential equation. Again, just remember that when you have got what is the difference between order and the exponent. So this Dava squared t, so here the square is on Dava, so hence it is the order of the partial differential equation. And when it is Dava x square, so x square, so that square is the exponent. Next we come to the topic of separation of variables, also known as variable separable. So what we actually do in variable separable is that we try to separate variables with respect to their derivatives. For example, in this on the slide, you see this differential equation dy by dx. Now this dy by dx consists of two functions. Okay, one, and you haven't come across. I think you haven't come across to solve a differential equation which involve two functions. So in this case, let's take that you have got two functions, which is one is a function of x and other is a function of y. So in order to differentiate, because f is in reserved for fx, so I have introduced another function which is g, which is a function of y. So this dy by dx is equal to the product of two functions fx and gy. Now you can see that there is a dy over here and there is a function of gy over here. Now there is also a derivative dx on left hand side, and then there is a function fx on the right hand side. Now what is required in variable separable is that you rearrange this differential equation so that the function gy is placed with dy, whereas function fx is placed with dx. So here you see that I have tried to make you understand that this dx is related to this fx and this dy is related to the function gy. Now when you look at the equation, you need to look at it and then you can separate it out. So the next step is that you bring all the terms that involve y on one side and all the terms that involve x on the right hand side. So when you do this, that is, you leave this dy over here and you have to bring this gy on the left hand side because you are trying to separate the variables. So when you include this gy, you bring it on left hand side, dy is already there, and then you bring this dx from the left hand side to the right hand side. The process is called separation of variables. So here I have directly placed the answer, but if you look at it, what I have done from the above step is that I have just brought this gy on the left hand side over here. So here it is multiplying, on the other side it will be division. So it's on the left hand side, this above equation will become dy over gy, and on the right hand side you will bring this dx on the right hand side, it will become fx dx. Now, when you have done the separation of variables, what is required from your side is to integrate both sides of the equation. And you know how to do that because you have been doing that since semester 1. That when you integrate this side, you will integrate it with respect to y, and when you integrate this side, you will integrate with respect to dx. So today, in whatever examples that we are going to do, we are going to follow the same technique that I have just explained. So at this point, when you have done the rearranging, that is, you have brought the x and y's separately, y's on left hand side including dy and x and dx on the right hand side, you can integrate both the sides easily if you have managed to do it correctly. So this is just a simple explanation of all the steps that you would be doing in the examples later on. So the first thing, that procedure that you will do in variable separable, is to separate the variables. So step one is that you look at the problem and then you separate the variable. You bring all the x including dx on right hand side and all the y's including dy on the left hand side. So as you can see in the first step, that's what I have wrote. Move all the y term including dy to one side of the equation and all the x term including dx to the other side of it. So you have done the first step, that is separation. Next step is integrate the terms. So you integrate the left hand side and you integrate the right hand side, and don't forget to put plus c, constant of integration, on any side of the equation. You just have to place that c on one side of the equation. I have already given you the explanation that when you don't have limits on the integration, then that's a indefinite integral. So the integration that you will be doing is the indefinite integration. Hence, you will be placing plus c on one side of the equation. Once you have integrated both sides of the equation, then you will rearrange the equation. Depending if you have got boundary conditions, then you will apply those conditions. Otherwise, that is your answer, and that answer in which your equation or your answer still contains that plus c, that is constant, that answer is called general solution. So up till now, whatever integration that you did in indefinite integration and you placed that plus c sign, that was a general solution. However, you also did one or two examples back in semester 1 and at the start in the topic of area under the curve, when you solved for the value of c, that what is the value of c. So when you do the process to find out what the value of c is, then in that case your solution or your answer is called particular solution. We will do this example also. So let's just find out that whether you have you have taken in what I have just explained. I have got few examples on the left hand side, 5 examples, and what I want from you is that any one of you or perhaps why don't we do this today, that you can write it out maybe in the chat function, that for this equation dy by dx equals to y over x, what is fx in this equation? So definitely if you look at this equation, this term, the right hand side term, is fx and gy. So if you identify, if you look at this side, right hand side of the equation, then please tell what is fx over here. In all these examples, you're going to look at the right hand side of the equation. Okay? On the right hand side of the equation, let's say for the first example, you have got y over x. So here, one term is a function of x, which is x, and one term is function of y, which is y. But if I ask you what is fx, can you tell me that? What is fx? So fx over here is 1 over x. Fx is just a function which has got x in it. So if you look at right hand side of all this example, and especially for the first one, fx is 1 over x. Now fx is 1 over x, then the function of y would be, gy would be
1.
yes.
Yes.
Okay, so this is how you differentiate. When you will look at all these examples, you should be able to separate x terms under fx and y terms under gy. And once you have identified that which one is fx and which one is gy, you can place both these function fx and gy according to the formula. For example, in this case, the last column, can you see over here that dy over gy? So what is gy? Gy is just y. So I have replaced this by y. And here integral fx dx. So what was fx? Fx was 1 over x. So I have just placed fx value, that is 1 over x, in the integral over here. I hope this example is clear. Let's come to the second example. So in second example, you have got 3x square e to the power minus y. So I can separate this 3x square as fx and separate this e to the power minus y as gy. And when I have identified fx and gy, I can place them in this formula, which is integral dy over gy, function of gy is equals to integral fx dx. So now, since I have identified fx and gy, I can place it in the formula. And if I place them in the formula, gy is g function of y e to the power minus y. Okay? And that means it is lying in the denominator. And if I bring it up in the numerator, the power will become positive because it is dy over e to the power minus y. So I have just brought it up in the numerator and made the power positive. And on the other side, I need to place fx times dx. So my fx is 3x square. So my integral becomes 3x square dx. I hope this is clear. What you are looking at is you are looking to solve it in terms of variable separable. Okay? And what you are looking at is to solve the equation with respect to bringing it in terms of y. Y equals to, okay? So when you are talking about in terms of y equals to, here what we are trying to do is to solve a differential equation. When we are trying to solve a differential equation, there are various ways, okay? So in this case, what we are trying to do is to bring the like terms on one side of the equation, that is y terms, including dy on the left hand side, and x term including dx on the right hand side. So based on that, if I come to my third example, here dy by dx, and you are already aware what is dy by dx. dy by dx is the slope. So this dy by dx is equal to y plus 1 divided by x minus 1. Now based on whatever information I have given to you, that you have to rearrange and bring like terms on one side. And all you have to do is once you have identified the fx and gy, then you replace it in the standard formula. That makes it, in this case, it is dy over y plus 1 equals to dx over x minus 1. Now, if you look at the last column, it is easily solved now. It is in the state that you can solve it because now you can use the standard table. Okay, if you were looking at just over here, the first column, and I ask you to solve it for y, you would be thinking, okay, we need to solve it for y. That means we need to integrate. So what I can do is I can bring my dx over here. Okay, fine. But then what about this e to the power minus y? Because then if you bring your dx over here, your equation will become y equals to 3x square e to the power minus y dx. In this case, you will have to do something on this e to the power minus y too. Why? Because on the other side there is a dy. And when you will integrate this dy, you need to do some process on this term which is lying on the right hand side and it contains y. Now, this is where the thing will get complicated, and in order to avoid that complication, the simplest procedure is that when you are given a differential equation, then what you should do, the first step is to separate out the variables. Bring all the y including dy on left hand side and bring the x including dx on the right hand side. When you have done this and you will integrate both the side of equation, hopefully when you do the separation correctly, the integration term will become easier because now you can use the standard table. Coming to the next example, it is y squared dy by dx equal to x. So here y square is already on the left hand side. So all you need to do is first to identify fx. So if you identify your fx, it is x. Okay. And what about your gy? So gy is already on the left hand side and it is y square. Last column will become y squared dy is equals to integral x dx. Similarly, in the last example, you have got dy by dx equals to e to the power 2x plus y. Now, you can break this exponential term into 2 because it is in the power, it is 2x plus y. You can break up e to the power 2x multiplied by e to the power y. When you have break up this term e to the power 2x multiplied by e to the power y, when the bases are same, powers are added. So you can see how we got this answer. But now you can separate it as bring this e to the power y on the other side and bring this dx over here. So it will become e to the power 2x times dx. So you look, your fx is e to the power 2x because it involves x, and your gy is e to the power y. Once you have got this, you can replace it in terms of the formula, which tells you that integral dy over gy, which in this case is e to the power y, equals to integral fx, which is e to the power 2x multiplied by dx over here. So these were 5 examples showing you how to separate out x variable x term and the y terms. Now with this we come to our first example, which is find the general solution of dy over dx, which is y over x. I have just given you this example, the first example. This is the first example that I have given you. Now, this question is different than the previous that I have been asking in integration. Why? Because it is not saying determine, evaluate. It is saying find the general solution of. So normally in variable separable, when you are asking the question, it generally starts with this statement: find the general solution of. So one of the clue is that when you look at the equation and you find the general solution of, think of it is as variable separable. So find the general solution of this dy by dx equals to y over x. So in order to find the general solution, I have explained those 4 steps in the previous slide. The first one was separate the variable. So the separate the variable means on the right hand side you separate out the x and y's. So fx is 1 over x and gy is equals to y. This is what we did in the previous slide. So now the first step is complete, that we have separated the variables according to the fx and gy. The next step is, after separation, integrate the terms. So after separation, we need to put these fx and gy according to the formula, and when we put it according to the formula, it becomes this. Integral dy over gy, so gy is replaced by y, is equals to integral fx is 1 over x and dx is there. Now you can integrate both the sides easily. Why? Because you know that when you integrate dy over y, your answer will be log y. Remember the standard formula? And for the other side, when you integrate dx over x, your answer is log x. Now this is the standard formula that I have been using those tables. So you should now be, it should be on your you should be able to, by actually seeing it, you can recall that it is log y and log x. So the answer to this side is log y is equal to log x, and since it is indefinite integral, that is, there is no limit on integral, so hence we need to have plus c. And we don't need to add plus c on both the sides of equation. Remember we talked about this, that we only need to add this plus c on one side of the equation. So answer to this side, left hand side, is log y, and answer to right hand side, dx over x, is log x, plus c is representing the process of indefinite integration. So plus c is representing that. Now what I can do is that I can rearrange this equation and I can bring the log terms on one side. So in the next step, you see I have brought this minus log x on the left hand side, so it will become minus, because here on the right hand side it is positive, and when I bring it on the left hand side it will become negative. So my answer is log y minus log x equals to c. So my value of the constant, so if I have to determine the value of constant, my answer is divide log y by log x and I'll get the answer c, or the value of the constant c. So my general equation, this is the general equation, this is the general equation, and that is the solution, general solution. So the value of the constant is log y over log x. What I can do is that I can replace this value of c in this equation. So when I replace this value of c in this equation, my answer will become log y minus log x plus log y over log x. Now if I know the value of x and y, if I know the value, let's say I know the point 0, 1, then I can find the value x and y, and because of this I can calculate my value of constant c, and I can place that value of c over here in this equation. We'll come to this problem, I think in problem 6 we'll find out what actually the value of c is. So when we have put in the value of c, then it is called particular solution. When we leave the equation in terms of this constant c, then it is general solution. Let's come to another equation, example, which is find the general solution of, so again, They are asking you a general solution. They are not asking you to determine, to evaluate, okay? They are asking you find the general solution, which is normally used for when you are trying to solve a differential equation with the help of variable separable. So in this case, your question is why dy by dx minus 3 equals to x. So if you look at it, the first thing that you should do is to separate out the variables. Bring the y's on one side and x on the other side. So the first step is to separate the variables. So if you see, I have brought this minus 3 from left hand side to the right hand side, and it makes the equation y dy by dx equals to x plus 3. The other thing that I need to do is to bring this dx from the left hand side to the right hand side. And when I do that, this is how it becomes. Okay, so this is just a verification that this equation is actually you are seeing is like this. It is the way it is arranged, but if you look at it, it is actually this equation. And what you can do now is to place these function fx and gy according to the standard formula. So the formula says that fx is x plus 3 and gy is 1 over y, because here it is gy is 1 over y. So now if you replace this fx over here and this gy over here in the next step, you can integrate it. So if you look at it, if you place your dy over 1 over y, your y will come up as a numerator. So it is y dy equals to fx. Fx is x plus 3 dx. Now it is very simple to solve because you know that integral y dy is y square by 2. Remember, it is n plus 1 over m plus 1. So y, 1 plus 1 is 2 and 1, so it will be y square over 2. The answer of this side is y square over 2 equals to, you can separate this out. So this will become x square by 2 plus 3x plus c for the constant of integral. So the answer to this part is y square by 2. And why we are getting this y square? Because remember, in integration, when you have got a to the power n and you integrate that, then it becomes a to the power n plus 1 divided by n plus 1. So that makes this as y square over 2. And this integral x will become x square by 2 plus integral 3 dx is 3x. And because it is indefinite integral, we have placed this plus c, or the arbitrary constant that you have to place. So in this case, when you have got y dy, it will solve out as y square over 2. Now see the difference. Earlier when you were doing integration, it was never y over here. It was always integral dy. And when you integrate dy, you always get answer y. Okay? Now, what you are seeing is that you are doing two integrations. So you are integrating y also and you are integrating x also. Earlier, you were just integrating right hand side based on x. That is the difference in what integration you were doing before. Now you are trying to solve the differential equation dy by dx, and hence you will perform the same procedure on the left hand side too. Hence you have got answer y square by 2, and for this part x square by 2 plus 3x plus c. The next step is what I have done is that I have multiplied this whole both the side by 2. So when you multiply this equation by 2, this 2 will cancel out, and what will be left is y square. What here is again 2 will be cancelled out with this 2, so you will get x square. Because we have multiplied by 2, so it will be 2 times 3 is 6x, and this will become c, 2c. So the constant will, when multiplied by 2, will become 2c. Now the reason I have changed it to d is that normally you would like to simplify the things. It could be the case where you leave it as 2c. It is all right. But normally what we do is that we say that when you have got a constant and you multiply any number to a constant, it is still a constant. Okay? So rather than writing 2c, I have just written as d. And d is again a constant. So any value multiplied by a constant will still yield constant. So hence this c is replaced by d. Now my objective is to find the general solution, which I have done, but it should be giving me a value of simple y, not y square. You have already done problems throughout in semester 1 where you were finding the value of x, not x square or x cube. Okay? So in this case, what I have done is that I have taken the root of both the side, and when I take the under root on both the side, this y will come out and it will yield me y, and on the other side the under root sign will remain, and all the terms on the right hand side will still remain under the under root sign. I hope this is clear. So for your understanding, I have explained this. Okay, so whatever I have just told you, it is all written there so that when you are looking at the solution again, you will come to know of what I have just explained.